Chapter 4 has to do with forces in one dimension or one direction. That means we're only looking at forces either in the vertical direction or the horizontal direction. We're not dealing with angles yet. Okay, we are going to start dealing with forces at an angle in Chapter 5. So you'll take a combined exam over Chapter 4 and 5. Just a little heads up. So this will be a little bit of a longer unit. But we're going to cover Chapter 4 first. So forces in one dimension, and then we'll move on to 2 dimensions. Okay, so can anyone tell me in regular plain terms what a force is? What might be something that describes a force? It's units or newtons, yes. But in very general terms, if I apply a force to something, what am I doing to it? Yeah, I'm trying to move it. Okay, a force is a push or a pull exerted on an object. Very, very plain words. It's a push or a pull exerted on an object. Okay, and forces are always labeled with a capital F. Okay, we see our capital F up there. Forces are labeled with a capital F, and then we have a subscript for it. Okay, so F sub G, F sub N. It always has a subscript that goes with it that labels the force for us. Okay, but it's always a capital F. So forces in very plain terms are a push or a pull exerted on an object. When we talk about forces, how does a force affect the movement of an object? What can applying a force do to an object? What's one thing that applying a force to an object, what can it make it do? What'd you say? Move in a certain direction. Good. It can change direction. What else could it do? What about stop it or slow it down. What else? One more.
Change direction.
Change direction or speed it up. Okay, it can speed it up, slow down, or change direction of an object, depending on where your force comes from. Okay, we have the ability to apply a force to stop something, to speed it up, or to change its direction. Okay, so forces can do lots of different things to an object. Okay, when we talk about forces and we talk about the system is going to be the object, or whatever it is that's being manipulated, we call the system. Okay, whereas the object that's doing or that's applying the force is called the agent. Okay, so we've got a system and we've got an agent. System is what's being manipulated. The agent is the person, thing, object that's doing the manipulating or that's applying the force. Okay, so if I stand here and hold this book or lift this book, what's the system and what's the agent? System is the book, agent is me, right? I'm applying this force to lift the book, to hold the book even if I'm not moving, even if I'm just holding this book, I'm still applying a force to keep it off the ground, right? To counteract gravity, I'm still applying a force. Okay? So there's 2 overarching kind of umbrella types of forces that we're going to talk about. The first of which is called contact forces. Okay, contact forces. What might contact forces mean? Yeah, any type of force that comes in contact with the object. So a push, a pull, holding something, anything that's in contact with that system, we consider a contact force. Okay, our other type of force is called a field force. So field forces are opposite of contact forces in that they are not in contact with the object. Okay, can anyone give me an example of a field force? Some sort of force that acts on an object that doesn't have to touch it. Yeah. Gravity. Good. That's a really, really main one. What else? Any other examples?
Wind.
What'd you say?
Wind.
Air resistance, kind of. Air resistance still technically comes in contact with the object when it's falling. But right idea? Mm-hmm.
Magnet.
Magnet, good. Magnet and gravity are the two major field forces that we think of. We will deal a lot with the gravitational force. We don't deal much at all with the magnetic field, okay, or the magnetic forces. Okay. So these are forces exerted without contact. Sorry, we talked about that. But if I drop my textbook, okay, which I'm not going to actually do. If I drop my textbook, is there some arm that comes out of the floor to pull it down to the floor? No. Yet it still falls, okay? Gravitational force is not a contact force. It doesn't touch things. It doesn't physically touch things to pull them down. Yet it still falls, okay? So other field forces we talked about were the magnetic force was a big one, okay? We're going to move on today to drawing these diagrams called free body diagrams, but we'll get here in just a second. Okay, I'm going to have you fill out this table of all different types of forces. All right, we're going to start with something called free body diagrams. All right, and a free body diagram is a pictorial model of our system, of our whole entire force diagram. Okay, when we make our free body diagram, we want to make sure we put down every single force that's acting on the object. We want to identify every place it touches the external world. So we're talking about every single force that touches that system. Okay? So let's start talking through this diagram here for just a second. On our system, we've got some sort of object, in this case a book, that's at rest on a table. Okay? And this person is applying a force in the rightward direction to try to push this book. And we've got three forces acting on it. We've got this force of the Earth's mass, or also called force due to gravity. On our book, we've got a force of the table on the book, and we've got this applied force of our hand on the book. Okay? And so we've got three different forces here. If we don't have anything opposing that sliding motion, we don't have anything opposing that sliding force, that means we have no frictional force. Okay? We don't see anything here in our force diagram or our free body diagram that's opposing the motion. That means, in this case, they say there's no friction. Okay? So those are some things we're going to have to consider when we look at drawing our diagrams. Whenever we draw these diagrams, and this right here is called a free body diagram. Whenever we draw the diagram, we draw them as vectors. We draw our forces as vectors because a force is a vector. It needs both magnitude and direction, right? Those are two things that a vector needs to have. Some of you forgot that on your test, okay? Vector needs to have both magnitude and direction. When we talk about our vectors here, we have to draw them to scale or a proportional scale, right? If one force is twice as large as the other, that means we need to draw our vector arrow twice as large as the other, okay? And that's really important in our free body diagrams so that we can see our overall net force here. Once our forces are all drawn, we can identify the object or the system as a dot, and that's what you'll see me do most of the time. I don't take the time to draw the actual object or what it looks like. We just identify our system as the dot, and we draw all of our forces from that dot, okay, or from that system. Okay, any questions so far? Okay. We know is acting. We have to draw these to scale. This is not a scale that we have to get out our ruler and draw them, centimeters to newtons type of scale. These are just a proportional scale. So if one's twice as big, you need to be drawing it twice as big. The last thing that we need to talk about is that they have to be drawn away from the object. So we don't have our applied force here that looks like this, okay, that's a big no-no, drawing it into the system. All of our forces should be drawn outward from the system. So if our force is going to the right, it needs to start with its tail at the system and move toward the right. Okay, forces are always drawn away from the diagram. So our forces have to be drawn away. That's a really, really, really important thing for you to understand, okay? Because we have to be able to view rightward forces and leftward forces in a very, very clear way, okay, for our overall goal to work out, okay? So let's go ahead and try to draw this free body diagram of this book accelerating to the right on a table, okay? So I'm going to go ahead and draw my system. Here's my dot. Here's my book. Okay. We know it's accelerating to the right. And we're asked to include friction. We are told to include friction here. So first and foremost, this book does not escape gravity, right? We still have gravity acting on our object. And we're going to label gravity as F sub G. That's our force due to gravity. Gravity is always pulling down that object. Okay, it's pulling down the system. Is the book, however, in a free fall in the downward direction? No, it's sitting on the table, which means we've got some sort of upward force that's causing that book to stay upward. Okay, and that force is called the normal force. And we're going to talk about that when you fill in your table here in just a second. But most importantly, we want to look at this fact that it's accelerating to the right on a table. If it's accelerating, we know that our applied force has to be to the right because it's accelerating. So it needs to start here and go to the right. And we just label that as an applied force, so I usually label them as APP. Okay, because it's some sort of applied force. Okay, if we know that our book is moving to the right, is our frictional force larger or smaller than our applied force? Smaller, right? If I am applying a force and I'm applying enough to overcome friction and accelerate it in the rightward direction, I have to have a frictional force that's smaller than my applied force. So we draw that proportionally smaller. Okay, and we label our frictional force as F sub little f. Okay, so this system has four forces acting on it: an applied force and a frictional force, and the gravitational force and the normal force. Is our book moving upward or downward in the upward or downward direction at all? No. So this up and this down force, the gravitational force and the normal force, should be equal to each other because it's not moving in the upward or the downward direction. Okay, those two have to be equal. Okay, so let's try this next example. A book sliding to the left on a table, and we want to ignore friction this time. Okay, so we've still got a gravitational force, and we've got to counteract that with something called the normal force, which we'll talk about here in a second. Our book's sliding to the left, so in this case, which direction does our applied force go to? The left. Good. And you could call that F push, F sub P, whatever you want. You could call that whatever you want. I usually label it as an applied force because something has to be applied. If we're ignoring friction, do we have any other forces we need to put on our diagram? No, this is essentially a frictionless diagram. So a frictionless table or system or whatever we're looking at here. So we're going to ignore that. Okay? These subscripts that go with our symbols here, F sub little f, if you can't see that, F sub capital N, F sub capital T and F sub little g, those are very important subscripts for you to have. Those are ones that can never change. You don't get to pick what the subscripts are for friction or normal force or anything like that. So those are ones that have to stay. We don't use force of the spring very much, but tension force we use a lot. We don't use thrust very much, but F sub little g for force due to gravity. Those are all subscripts that can't change. Okay, you have to use those particular ones because they're universal. Okay, so let's talk through these forces just pretty quickly here. Our frictional force, something that's important to remember, or the most important thing to remember, is that it opposes motion. It opposes anything that slides. Okay, and sometimes we'll be told to ignore friction. Sometimes we're told to include friction. You just have to read what your problem is telling you. But it doesn't mean that friction always goes to the left or always goes to the right. You just have to make sure you understand which direction your object is going, in which case your friction would go in the opposite direction of that. Okay, so friction doesn't always necessarily go to the left or always to the right. You have to pay attention to which direction your object is going. Friction opposes that. Okay, friction will always be a horizontal force. Okay, you won't ever see friction acting in the vertical direction. Okay, I don't know that I've ever seen an example in which that's the case. But it always goes parallel to the surface. Okay, and right now we're dealing with surfaces that are flat. Eventually we'll deal with inclined surfaces, in which case your friction would go parallel to the surface in that case as well. Okay, the normal force is a contact force exerted by the surface on an object. So in that first diagram that we saw, right here, our table is exerting a force on the book. So this force would really be called F sub n. Okay, it's the force that's exerted by the surface upward on an object. Okay, so we would relabel that force as F sub n, our normal force. Okay, the normal force is always exerted perpendicular to the surface of whatever is resting. Okay, it's always, always, always perpendicular to the surface. Okay, spring force we don't need to get into quite as much. Tension force is a pull exerted by a string, rope, or cable. So this is when something is hanging from a string, hanging from a rope, from a strap. Anything that's hanging with a cord or a cable attached to it has this tension force. Okay, so just pay attention to the wording of problems to see what sort of an upward force you're going to have. Tension force can be both vertical or horizontal. So if you've got two objects that you're pulling something with a string or something like that, pulling a wagon or pulling two boxes connected by a string, you'd have a tension force there as well. Okay, and the very last thing I want you to see is our gravitational force. Gravitational force always, always, always acts straight down, okay, toward the center of the earth, straight down, and it's always labeled F sub g. Okay, F sub g always acts straight down. Do any systems escape gravity? No. Okay, you're always going to have a gravitational force. Okay, you can't go wrong including that gravitational force. So in this diagram right here, we would label Earth's mass on book. We would relabel that as F sub g. Okay, so if we were looking at this diagram and labeling it with the forces that we just learned, we would have a normal force, we'd have a gravitational force, and I would rename that force as an applied. Okay, you can label it as force push, force hand, force whatever you want, but I usually label them as applied forces. Okay? All right, let's talk about Newton's first law here. How many laws does Newton have? 3, good. So we're going to talk about his first law here that says an object at rest will remain at rest. An object that's moving will continue to move in a straight line with constant speed if and only if the net force on that object is 0. Okay, the first section of this law is very commonly heard and kind of the most important. An object at rest will stay at rest. An object at motion will stay in motion. Okay, that's unless it's acted upon by an outside force. Okay, so this is with no friction, with no air resistance. This is perfect physics world type stuff. But essentially, if I begin an object with some force, with some velocity, it will continue to move at that velocity for eternity unless acted upon by an outside force. Okay, so unless something else comes and stops it, it will continue to move. Okay, this first law has a nickname. Can anyone think about what that nickname is? It's got a nickname called the law of inertia. The law of inertia. Okay, so this is the nickname for Newton's first law, the law of inertia. And what inertia in itself means, inertia means the tendency to resist change. So as something is at rest, it wants to stay at rest. It does not want to change. It wants to stay at rest. Just like an object in motion wants to stay in motion. Okay, it resists that change. Object at rest tends to stay at rest. An object in motion tends to stay in motion. So it wants to resist change. Okay, so that law of inertia is very important for you to remember for Newton's first law. Okay, so we talked about what happens if there's a non-zero net force, right? Unless something's acted on by a non-zero net force. What's it mean to have the net of anything? What's it mean to have a net profit? What? Overall, yeah, total, sum, right? So your net force is going to be the sum of all forces acting on an object. Okay, it's the total, it's the overall sum of what's acting on an object. Okay, sum of all forces acting on an object. We consider an object to be at equilibrium or have a net force of 0. So I'll write that up here. Equilibrium means net force, so F sub net equals 0. Okay, and that's how we write our net force, is with F sub net. F sub net. So when we're object at equilibrium, it's at rest or it's moving at constant velocity. It has a net force of 0. Okay, and that's a really, really important concept for you to understand here. When an object is moving at constant velocity or it's at rest, we've got a net force equal to 0. So when we look at these free body diagrams of 3 different systems here, we're going to calculate the net force of our system, which is our overall sum of forces. We're going to take our right forces minus our left forces, or our up forces minus our down forces, which would give us our net. Okay, that's why it's important to draw these to scale and in the correct direction, because it gives us a good diagram of what we're looking at here. So calculating the net force is the overall sum total. Here we've got a situation in which our force 1 is going to the right at 100 newtons, and our second force is going to the left at 100 newtons. Okay, which means our net force overall, if we take right minus left, our equation would look like this. F net is equal to F1, that's our rightward force, minus F2, which is our leftward force. So we would then plug in our values. 100 minus 100 equals 0. Okay? I know it seems simplistic just by looking at the diagram. You can tell that those are going to cancel out, but it's important for you to get into the habit of making this equation. Okay? You're always going to make that equation. F net equals right forces minus left forces. Okay, does that make sense? Right forces minus left. So let's look at our second situation here. Our equation would look like this. F net equals rightward forces minus leftward forces. So what rightward forces do I have? F1. Do I have any more rightward forces? F2 is going to the right also, isn't it? So plus F2. Do I have any leftward forces? No, so you can either stick in a -0 or you can just leave that out. Okay? In which case I would plug in my numbers and I take 100 plus 100 and I get 200 newtons to the right. Okay? They didn't draw a free body diagram with this system. Okay, if they did, it would look like this, F sub 1 and F sub 2. It would be 2 arrows added tail to tip on each other. Okay, they would label it F1 and F2. They didn't bother with a full free body diagram. They looked at them separately. Okay, and then for our final system, our net force equation would look like this. What's our rightward force here? F1. And what's our leftward force? F2. So that means to find my F net, I'm going to take 100 minus 200. And that gives me a negative 100 Newton force, net force. I could either keep it as the negative or I could write it 100 newtons to the left, okay, with an arrow indicating my direction. But forces are vectors, so they need to have both magnitude and direction. We have to have both of those included. Okay? Okay, Newton's second law comes with words and it comes with an equation. Okay, so acceleration of an object is equal to the sum of the forces, which is F net, divided by the mass of the object. So that's this equation right here. This equation is almost always manipulated to look like this. F net equals mass times acceleration. That is really, really an important equation for us. F net equals mass times acceleration. With it. Okay. What are the units for force? I think we already talked about it a little bit, but what is it? Newtons. Okay? And since this is the unit that would come out of this equation, right? Mass has to be in kilograms, acceleration has to be in meters per second squared. Instead of having to write this unit every single time we solved for a force, they abbreviated it and called it a Newton, which is indicated by a capital N. Okay, it has to be a capital N. We want to find the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared. We want to find the net force. So knowing what we know about Newton's second law, we're going to take F net equals mass times acceleration. Net force is what we're solving for here. We were given our mass and we were given our acceleration. Are our mass and our acceleration in the correct units?
No.
Why not?
Yes.
Yep, kilogram times meters per second squared is equal to 1 Newton. So our mass has to be in kilograms, our acceleration has to be in meters per second squared. That's the case here, so we're good to go. Okay, which means our overall net force here is 4,900 newtons. Okay, it's important for you to realize that the net force is equal to mass times acceleration. Because when we start looking at free body diagrams and we have a problem that looks like this, F net equals F applied minus force of friction, something like that. When we set up our net force equation here, just like we've been doing, we can substitute in F net for mass times acceleration because we know that F net is equal to two different types of things. Okay, F net is equal to mass times acceleration. It's also equal to the sum of all forces. So that's going to be a big substitution for us that we're going to do a lot. Okay, does that make sense? If we know F net is equal to mass times acceleration, it's also equal to the sum of all forces. That's going to be a substitution that we use a lot. Okay? We'll get there, but I want you to see the connection between those two things. You have two different ways to solve for the net force of a system. Two different ways. Okay, what's the net force required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? So here we have to use our kinematics and our force equation. So kinematics you're not done with. Okay, I think I told you that it was going to be a year-long thing. Okay, you're not done with kinematics yet, so we need to start looking at this problem to solve for something. All right, what other variables are given to us here in our problem? What's this 1,500 kilograms tell us? Mass. Yeah. In kilograms, right? So 1,500 kilograms is our mass. We need to bring it to rest. So it needs to come to rest. What kinematics variable does that tell us? Velocity final. V sub F is 0. Okay, it comes to rest from a speed of 100 kilometers per hour. So that means our initial velocity is what? 100 kilometers per hour. Is that the correct unit that we need anything to be in? We need to be in meters per second. So we can use that shortcut. Times 0.2778. And what does this value tell us right here? Distance final. Good. So we know we have to use our kinematics equation, but what variable do we need to solve for?
Acceleration.
We had to solve for acceleration, right? So if our overall goal is to find F net, we need to use the equation F net equals mass times acceleration. We're given our mass. We want to solve for F net, so we've got to find our acceleration somehow. We were given the kinematics variables to do that. So what kinematics equation can we use to solve for acceleration when we don't have time? The last one. We can use VF squared equals VI squared plus 2A dF minus DI. Okay, so 0 squared equals 27.78 squared 2A 55. So can someone raise their hand and tell me what value you got for acceleration? Yeah, Nate.
That would be negative 7.01
Okay, and what's our units for acceleration?
meters per second squared.
Meters per second squared. Good. Do we agree, therefore, with our acceleration?
What was it?
Negative 7.01. Does that make sense that our acceleration is negative? Yeah, we're moving in the positive direction and we're slowing down. So our acceleration and our velocity shouldn't match. So now we can take our F net equation and plug in mass times negative 7.01 and give us a net force equal to negative 10,515. Is that what you said? 519? 515. Sorry. And what's our units for force? Newtons. Okay, good. What's the negative tell us here? Yeah, it's coming from the left, right? Or it's going left. It's opposing our motion. And since our motion is moving in the positive direction, that means our force that's required to stop it must be moving in the negative direction. Okay, it could be a frictional force, could be something, whatever, but our overall net force has to be in the negative direction. So we've got to have more friction than our applied force, or we've got to have a greater amount of applied force in the opposite direction to make that come to a stop. Okay, so this is our net overall sum of forces. So that means that our applied force minus our frictional force is going to equal this negative number. So our leftward force is greater than our rightward force in this case. Does that make sense? Okay. So we already talked about the fact that something moving at constant speed has a net force equal to 0. Right? When something's moving at constant velocity or constant speed, F net is equal to 0. But now you can see why using Newton's second law. So F net's equal to mass times acceleration. What's the acceleration of an object that's moving at constant speed? 0. So anything times 0 means our F net is going to equal 0. So there's a mathematical representation as to why that is true. Okay, that's telling us why that's true. If it's moving at constant speed, that means there's no acceleration, which means it has a 0 net force. Okay, just like something is at rest. If something's at rest, it's not even moving, which means it has no acceleration, which means our net force is 0. Okay, so there's two situations in which you have a net force equal to 0. When an object is at rest and when you're moving at constant velocity. Those are important for you to realize. Very important. Okay, do we have like a good head nod that that's what you understand? Okay, that's something that you can't forget. Okay, that's going to be used.